All right, we've taken derivatives of natural log. Now we want to go backwards. We want to be able to integrate using the natural log. The problem that we run into with a problem like this, the integral of 10 over x dx. In the old days, we would have said that that was the integral of 10x to the minus 1, and then we would have added 1 to the exponent, which would give me 0, and divide by the new exponent, and that's undefined. We can't do that. But now we know that the integral of 1 over x is the natural log of x. So what I can do, I can just pull this 10 out front. It's the integral of 1 over x dx, and I know that this is the natural log. And so this is just equal to 10 natural log of x, but I can't take the natural log of a negative number, and so I fix that by adding absolute value bars and plus c, as always. Now, of course, it's not always that simple. Find the integral of x squared over 3 minus x cubed. These problems almost always work if you will set the denominator equal to u. So I'm going to let u equal 3 minus x cubed. Take the derivative of both sides and solve for dx. Now when I rewrite my integral, I have x squared over the denominator is u now, and dx became this, du over negative 3x squared. And it's always nice and convenient when your x squared term, or whatever was on your numerator, cancels what's now in your denominator. And so this integral turns out very nicely. I have negative 1/3 times the integral of 1 over u du, which I know is just the natural log of the absolute value of u, plus c. But I can't leave it as u. We'll replace it with my definition of u, which was 3 minus x cubed. Making sure to use my absolute value bars. Don't forget your plus c, and it's done. This worked really nicely because the numerator was the derivative of the denominator, but we're not always that lucky. For example, find the integral of this polynomial over x plus 5. There's no way that the numerator is the derivative of x plus 5. So what we can do is we can simplify this problem by doing long division first. So just like we would rewrite natural logs before we would take the derivative, we can rewrite division problems before we try to take the integral. So let's do some classic long division. I have x cubed. I'm going to fill in my placeholders. There's no x squared term. Minus 6x minus 20. And I'm dividing by x plus 5. Okay. How many times does x go into x cubed? X goes into x cubed x squared times. So I line that up with the x squared column. And then I'm going to multiply x squared times x plus 5. That will give me x cubed plus 5x squared. But I'm going to subtract that term. And that gives me negative 5x squared. Copy over the rest of it. Oh, that was bad. That's a 0. Now I'm asking the question, how many times does x go into negative 5x squared? The answer is negative 5x. And then I'm going to multiply negative 5x times x plus 5. That will give me negative 5x squared minus 25x. But I am subtracting that line. And I'm going to run out of room. Everything's fine. 19x minus 20. How many times does x go into 19x? The answer is 19 times. And so I'm going to put 19 here. 19 times x plus 5. I'm going to squeeze it in here. Everything's fine. 19x. I found out one time that I could scroll on here, but I've never figured out how to actually make it do it. That obviously did not work. 19 times 5 is 95. Subtracting that line, so that's going to cancel out. 20 Negative 20 minus 95 will give me minus 115. That's my remainder. And so my function becomes x squared minus 5x plus 19. My remainder was 110, negative 110, over my divisor. And oh, by the way, I am integrating that. So I will integrate as normal for these first three terms. That will be x cubed over 3 minus 5x squared over 2 plus 19. And then this term, I'll follow my natural log rules. If I set u equal to x plus 5, nothing changes, right? du is just equal to dx. And so I can say that this is minus 110 natural log of the absolute value of x plus 5. Don't forget your plus c. And that, long and gross as it is my answer. Let's do one more. Find the definite integral. And once again, I'm going to set my denominator equal to u. There's not really a convenient way to rewrite this one, so we'll just go straight to it. U is equal to x plus 1. Take the derivative, and that's just equal to dx. And so when I rewrite this, I'm going to change my limits of integration. If I plug 0 into this function, I'll get 1. If I plug 1 into that function, I'll get 2. X minus 1 stays there, x plus 1 is now u, and dx is du. I have a problem. My x minus 1 in the numerator did not cancel out. When that happens, when x doesn't cancel out, what you have to do is go back to your definition of u. I can solve this for x. I can say x is equal to u minus 1, and then I can use this definition to plug in for my x here to get it in terms of u. So when I do that, I'll get the integral of, from 1 to 2, of u minus 1, my minus 1 here is still there, over u du. This is the integral from 1 to 2 of u minus 2 over u du. And now I can split this up into two fractions. I can do this fraction minus this fraction. So this is equal to the integral from 1 to 2 of u over u minus 2 over u du. The integral of 1 minus 2 over u du. I think I'm finally ready to integrate now. So this will be equal to u minus, and then this right here is 2 natural log the absolute value of u. I'm going to evaluate that whole thing from 1 to 2, and that will give me 2 minus 2 natural log of 2, and then plugging in 1, I have 1 minus 2 times the natural log of 1. The natural log of 1 is just 0, so I have 2 minus 2 natural log of 2 minus 1. Final answer, 1 minus 2 natural log of